All right, question 22, right? Select the molecules that are polar. I think someone asked about this earlier. We were talking about the geometry, right? And so that's where understanding the geometry, the shape is really helpful here. So fluorine is the most electronegative. So we're pulling electron density away, we're pulling it away, we're pulling it away. Oxygen is electronegative, but not as electronegative. So because this molecule is not symmetrical, right? That'll make it polar because we're basically pulling electron density to the bottom half of the molecule, and that's going to create a little partial positive charge on the top and a partial negative charge on the bottom. So that makes this first one polar because we lack symmetry, right? Whereas on the second one, we've got chlorine matched with chlorine. So in this tug of war for electron density, right? In this tug of war for electron density, chlorine's pulling up, chlorine's pulling down, they tie because they're 180 degrees apart, right? So they cancel each other out. And then if we look along the equatorial positions, this one is a little bit harder to see, but I'll do an aside, right, to boron trifluoride. Boron trifluoride is also nonpolar because, right, fluorine, 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 those three fluorines, they're all pulling the same strength from the same point, and all of those vectors, they cancel out. So that makes this nonpolar. So the same thing actually happens here, right? I guess green doesn't show up too well on this screen. So this fluorine's pulling, this fluorine is pulling. All of those fluorines cancel out. And because of the symmetry here, that makes this molecule nonpolar. If I change the symmetry, right, if I just flipped one of those chlorines with a fluorine, and if I put a fluorine there, and then let's say I put chlorine here, right? So if I change the symmetry of this molecule, I would change the polarity because now this chlorine is pulling, but fluorine is much stronger. It's going to win in that tug of war, right? And the same thing here. These fluorines would pull and pull, and chlorine couldn't balance them out. So that lack of symmetry, right, would make this polar. So for three, yeah, for question for molecule 3, formaldehyde, is that polar or non-polar? All right, carbon and hydrogen are not, carbon hydrogen, that bond is a non-polar bond, but the carbon oxygen is, there's no symmetry. So yeah, this would be a polar molecule. Here, that vector is going to cancel out with that vector. So that would make this a non-polar molecule. We'll come back to this one because this one's a little bit tricky to see. And then the last one here, again, we don't have symmetry, right? This fluorine is not balanced out by chlorine, right? So that would make this molecule polar. The dichloromethane, if I redraw it a little bit, maybe it's easier to see. And in one of my classes today, people were convinced this is not the same structure. It is the same structure because we just have two chlorines around that central carbon. So I can spin this, and whether I draw it the way that it's shown or the way I drew it the second time, they're both the same structure. So I think it's easier to see here that, right, this chlorine is pulling electron density, this chlorine is pulling electron density. So in net, right, we're pulling electron density to like the upper left-hand part of the molecule. So that would make this one polar as well. So yeah, a lot of it has to do with the geometry, the shape of a molecule. Is it symmetrical or not? And to figure out if it's polar or not. All right, got to get going here. Yeah, so like the symmetry and how it's substituted. So in this case here, right, these two chlorines are 180 degrees apart, so they cancel out. These three fluorines are all equatorial positions, so they cancel out. The squiggly and dark lines are there to kind of help give us three dimensionality. So that's this bold line basically means this fluorine is sticking out of the page at you. This hashed line basically means that the fluorine is going back into the page. So it's kind of, here's the page, right? One is going out of the page, one fluorine is going into the page. That's what those bold and the dashed lines mean. They're trying to show you the three-dimensional shape of the molecule. And I don't know if Anthony, if that works for you, right, for the symmetry, right? Is the molecule symmetrically substituted or not, right? Is what we're trying to figure out. Yeah, exactly, right? If it's not symmetrically substituted, there's going to be a different magnitude of those forces, right? Like I've drawn here. So here we lose that symmetry, right? This is not symmetrical. And now I have fluorine 180 degrees from chlorine. So those forces are different strengths, right? This is a small force. This is a much bigger force. Fluorine wins in this case. Whereas here, chlorine to chlorine is a tie. Fluorine to fluorine, tie. Here, we don't have that symmetry. So we're changing, right, the imbalance of those vectors, or creating imbalance in those vectors, right? Bromine pentafluoride, right? So bromine has got 7 electrons, right? I've got 5 fluorines at 7. So, right, that's 35, that's 42 electrons. So I think we're going to end up with bromine. Right, there's 10 electrons right there. So I've got 32 electrons left. Right, there's 6, 12, 18, 24, 30. So 2 electrons left. Those last 2 electrons go on bromine. So we have 6 domains. So we're octahedral electron domain geometry. And then 6 domains. We need to have 6 hybrid orbitals. So we're going to be sp3d2. And the shape, right? Octahedral family, 5 bonding, 1 non-bonding. We're square pyramidal because of that for question 23. All right, question 26, potassium chlorate decomposes to produce oxygen gas. How many liters of oxygen gas are produced from 92.5 grams of potassium chlorate, right? So very similar to the problem we did in class. I think is potassium chlorate, KClO3, I think it's 122.55 grams per mole from the problem we did in class. Right, 92.5 grams. Someone tell me if that molar mass is wrong. We got to find moles first, moles of our solid. So 122.55 grams. It's our molar mass. So 92.5 divided by 122.55, right? 0.754 moles of potassium chlorate. We want to know how much oxygen is made, right? So you need to find moles of oxygen, then we can relate that to volume of oxygen. So All right, I know. There's my potassium chlorate. We go to the balanced chemical equation that tells us for every 2 moles of potassium chlorate, I'm going to make 3 moles of oxygen. So that's our conversion factor, right? 3 moles of oxygen out for every 2 moles of potassium chlorate in. So multiply that by 3 over 2, 1.13 moles of oxygen. Now we can go over and find the volume. Now we can use PV equals nRT. Right, we're looking for volume, so we can divide both sides by pressure, right? The volume of this gas equals nRT over P. My volume equals my moles, 1.13 moles. R, 0.0821 liters, ATM, mole, Kelvin. My temperature, all right, Kelvin equals degrees Celsius plus 273. So temperature in Kelvin equals 823. And my pressure, 1.05 ATM. All right, unit analysis, we multiply, moles cancel, Kelvin cancels, we divide, atmospheres cancel. We're left with liters, right? We should be left with liters. We're looking for a volume. Right, so 1 point times 0.0821 times 823, divide that by 1.05, and I get something like, I would say 3 significant figures, so I would say 72.9 liters of oxygen gas should be made. Hopefully that's a correct answer. Okay, 72.8 looks to be there. Yeah. So 72.8, 72.9. I'm not sure what I changed, but that looks to be the correct answer there. All right, the ketene problem, question 30. All right, if you came to office hours today, you got to hear about how I had to make ketenes all the time in grad school. And so that's why I was like, oh, that would be a funny structure because they're really reactive. So to figure out the orbitals that are used, right, in this structure, we need to figure out the hybridization of each of these. So carbon, this carbon has 3 domains, so that's sp2 hybridized. This carbon has 2 domains, sp hybridized. This oxygen has 3 domains, and so that makes it sp2 hybridized. So as we walk our way down the molecule, or up the molecule, I guess, hydrogen to carbon would be s orbital to sp2 hybrid. And then in our carbon-carbon double bond, the sigma bond would be sp2 orbital to sp orbital. The pi bond, right? Pi bonds should be easy because pi bonds, p orbital to p orbital. And then the carbon oxygen double bond, right? Sigma bond is going to be the sp orbital from carbon and the sp2 orbital from oxygen. The pi bond, again, p orbital to p orbital. And then if you want, right, the lone pair electrons are also in an sp2 hybrid orbital from question 30 on the extra practice exam that was uploaded. All right, and then Tina's question real quick here. I can go back to that somewhere here. Right, this should be super easy. Linear, I guess yellow doesn't show up too well. All right, linear, 180 degrees, right? Three domains. We're going to split a circle into three parts, right? Each part should be 120 degrees. Tetrahedral is a little bit tricky, right? 109.5 degrees. The trigonal bipyramidal also, here's the first one. We have two bond angles, right? So trigonal bipyramidal, from our axis to the equator, we're 90 degrees, and then around our equator, we're 120. And then octahedral, we're back to identical bond angles. Everything is 90 degrees, right? Axis to the equator is 90, and then around our equator, we've got four spots. So split that circle into four quarters, right? Around the equator, we've got four things. So we split that into four quarters, right? 90 degrees for each of those segments, yeah. All right, gonna stop the recording there.